Yeah, we asked that question before. I don't think people actually know what their compression is, because I know what our compression is, and if anybody claims to have the same compression, their car should sound the same, right? Jamie's car sounds completely different than everybody right now.
Hello, Mr. Dave.
Today, I guess what we wanted to wrap up all the camshaft chatter.
Yeah, I was kind of thinking that if I don't know if Brandon talked to you about the quiz idea, but just have the valve motion. Look at the valve motion chart. Talk about the jerk, velocity, valve bounce, lofting. Like just sum it up. Sum
Yeah.
up if you could do like a minute or less, just this is what you're trying to achieve. Different valve train systems have different limitations, and then camshafts are kind of put to rest for now.
I think you just summed it up, right? It's like yeah, what Jay
Well,
said, that.
well, we'd like to for the end user to be able to look at that valve motion chart and know what each thing is. So you've scribbled it on your iPad more than once since we started,
Yeah.
but just since we don't have a really fixed structure, we do talk and go in circles a lot.
But isn't that what car guys do?
Yeah,
Yeah.
yeah, but
It's the,
concise information. You know, when you look on a video on how to fix your refrigerator, it's fine. It's good to be able to find the one part of the 13-minute video of what you're actually trying to accomplish, and you don't have to hear about the dude's life story that's about to give some instruction.
well, if that instructional was available 30 years ago, it would have made life easier, right? But
Yeah.
my summary of it would be the valves are the epicenter, right? It starts there. The valves are limited by the bore, and then how, like, when you can open and when you can open the intake cam and when you can close the exhaust cam is all going to be in that 10 degrees before top dead center and 10 degrees after top dead center. Like that's where all the fitting of the engine building happens, really optimizing all the clearances. Fitting stuff, I think, is actually higher up in a lot of the considerations than optimal timing. You know what I'm saying? It's like the timing a lot of times is just the compromise. It's like the best we can make it perform, but it's not necessarily the ideal valve timing. It just happens to make a little bit more because it's getting more air, right? So there's trade-offs there.
Maybe we talk about the trade-offs where is it more acceptable to trade optimal open and close for or really open for air, right? In the case of uh, duration versus lift, where if you're space limited um, by one or the other, where's one more optimal than the other?
Well, the exhaust cam, there's more flexibility with the exhaust cam. Like you can adjust for a bad exhaust port by just throwing more exhaust duration at it a lot of times, right? But you really can't do that with the intake. Like if you try to opening the intake, if you make the intake too big, it will either open too early and smash the piston, or it opens so early that you have to carve a big chunk out of the piston and it just takes all the dome volume out of the piston. So like that's one issue of having to, when you go too big to gain the extra airflow, you're robbing real estate from the piston. You're doing weird things to the compression, right? So like people always have these high, like, we'll get into the full piston discussion down the road, I'm sure, but people like the high dome. um, they think it's cool for whatever reason, and that's just wrong. Like the flatter you can make that piston, the more volume and the flatter you can make that piston, the better that piston's going to be. And then one big consideration for the piston volume is going to be how deep the valve pockets are plunged, because that takes most of the volume out. The intake valve, especially in these K engines, are so big that when you clearance for the intake valve, it just takes out a lot of cc's right out of that piston. The deeper your piston pocket goes, the dome ends up being peakier in order to get the volume back.
What's the average CC of K series with good valve reliefs.
You want me to answer
You
that?
got a flat top piston with valve reliefs. What's the negative CC volume?
We want to use like all motor as like what do we want to use? We want to
Well,
use like a
well,
flat top turbo piston.
we're discussing some of the restrictions with the valve angle dictates the valve pocket, right?
All right.
So if you have an engine that when you get into some of these modern two valve engines, they have the intake valve is rotated fairly flat with the piston with a raised runner, and you don't have to run a lot of valve relief because the the valve is more flat with the piston.
Well, the valve
In
the depth of the valve relief is not so much the angle of the valve. The depth of the valve relief is like where did you open the intake cam? Where did you open the intake valve? Because
well,
ultimately the clearance we're talking about is like 7 to 8 degrees after top dead center. So the the question is where is the valve at 8 degrees after top dead center? Add your clearance to that, and that's where your pocket should be. But
well, going back to my question with a K series flat top, how much volume do you end up in just valve reliefs? I'm just trying to have a little contrast to the JZ.
I haven't seen a flat top. Like I haven't touched a flat top in forever, right? So if Jamie's messed with flat tops, he could tell you. I could tell you, like I know what the high compression stuff is, but if you talk about a flat top piston, valve relief shouldn't take out a whole lot.
Yeah, like less than 5 cc's.
Yeah, the turbo they're running smaller durations, so they're not, and they're smaller lifts, smaller durations. So the cam at 8 degrees after top dead center, it's not open a whole lot, so it doesn't need a whole lot of valve relief, right? Like these all motor drag race guys, they're running like the intake valve pockets like 260, somewhere around there, 250, 260. That's like a pretty big gouge out of the piston.
Yeah.
It's like here. All right, we're gonna go into AV chaos again. So depending, like if the intake valve opens real deep, you got to carve a big section out of the piston there. And in order to get that dome back, people end up having to push the height. You know what I'm saying?
Yeah, and your concern and/or problem with the dome is how it affects the propagation of the combustion.
Yeah. Speed bump. Obviously, like if you made the valve release very deep on both sides, then you could see how you just start wiping away
The dome.
the dome, and then as your pockets go down, and then your top ringland guts get pushed down because you
Yeah.
have a minimum clearance from the inside of the ring groove to the closest point of the pocket,
Right.
right? And so like you move the ring down, and now it's like all of a sudden you added a whole bunch of crevice volume into your compression calculation.
It's amazing you guys are able to get such high compression ratios out of those engines.
Well, the industry does not. I mean, on average, you're talking. I think we asked that question before. I asked it, I think, on my Facebook. Like, what is your compression ratio? And the answers I got were pretty spread. They advertise on what some of the companies advertise for compression ratio versus calculated compression ratios with the dome volumes on a lot of these shelf pistons just don't add up. So on average, like the industry standard for most all motor applications right now is probably between 9 and 11 cc's the dome volume for the average 90 millimeter drag race K all motor setup. So, I mean, Dave probably has a calculator in front of him. 9 cc's a dome volume at 99 millimeters of stroke. Um, I mean, we can do the math and see what that is, but it's definitely far off from what's being advertised.
Yeah, we asked that question before. I don't think people actually know what their compression is. because I know what our compression is, and if anybody claims to have the same compression, their car should sound the same, right? Jamie's car sounds completely different than everybody right now.
Right.
You already know we make some of the best street and race cams out there. But did you know we also carry all these essentials for your engine? From head gaskets to billet engine covers, if you're in the process of a rebuild, you're gonna need these. From top to bottom or valve covered oil pan, we've got you covered. Go faster.
Okay, if I was to summarize the whole from the user engine builder perspective, on the intake cam, I don't want to close it too late, right? I want to close it after bottom dead center, but I don't want to close it too late after bottom dead center. Like in the case of these engines now, I think we're closed, like the valve seating around probably 80 to 90 degrees after bottom dead center. So that the real compression stroke is probably only about 90 degrees, 100 degrees. The bottom half of the compression stroke is actually the cylinder still filling.
Right.
Right. So last time we talked about the inertia of the charge, it's still ramming in. Even though the piston is starting to move up, there's enough energy in the intake column where it just continues to just sort of freight train into the hole because it's got mass. So yeah, not the earlier you close the intake valve, the more compression it'll make, but then you'll start to see the higher the RPM goes, the earlier you close the valve, it ends up in a place where it's like a tractor cam, you end up a lot of bottom end torque. So the RPM is another thing that dictates like how much lead do you need to run in terms of opening the cam to make sure it has enough area under the curve to let enough air in. And then it's a delayed closing too, to allow more air in. But like the stuff we're dealing with right now is far from optimal because the piston speed's ridiculous.
You had mentioned as we went through camshaft stuff that the finger follower allowed for faster valve action.
Yeah.
Could you quantify that? We were talking about degrees of crankshaft rotation, and how different. If we say that a rocker arm system, a bucket system, and a finger follower system, could you assign a percentage of gain in valve action with one versus the other? Like, does the valve, can you get X amount more out of the camshaft? Because you just stated that in order to have proper filling, we let the intake valve stay open as the piston's on its way back up because your charge is headed in, and the charge has velocity, and it's this big air mass, and it's not going to change directions easily. It's going to change directions when the valve shuts, but for the most part, air is headed in the cylinder. So if we know that you have to fudge the valve timing to get high RPM cylinder filling, does a finger follower still offer you a reasonable increase in performance?
I would say having any rocker arm, whether it's mounted on a shaft or, like a finger follower, or if it's a overhead valve rock arm, any rocker arm is going to give you the ability to actually multiply the amount of lift that you get. So I would say the biggest advantage is with any rocker arm system, you'll be able to get more lift than any sort of direct actuation, like a 2J type of thing. Right. So like I may not have that much. We may have similar installed heights. I don't know do you know what the installed height is on the 2J?
1135. 135.
That's
13 3305. I think it's 33 millimeters.
okay. So that's like a B series engine, like 33.5. Right. Well, B series engine, you can get 550 out of the stock configuration.
Yeah. And that's commonplace.
Huh?
That's commonplace.
Yeah, like all of our new TLRC stuff is all 540 intake, So I would say the biggest gain is the net increase in net lift with the rocker arm, just the multiplier.
Right on.
But we also said that you can't use traditional like OHV rocker arm calculation to get an accurate valve motion. You can only get an idea of the net lift with the rocker arm ratio with the over it the finger follower stuff.
Going a step further and talking on the rockers, looking at the TLRC versus some of the K technologies. So slider versus roller, right? The B factory B series being a three lobe slider, which we've then converted to a twin lobe roller, versus the K series from OEM being a roller system that in some of our stuff we've pushed to a slider. Maybe we can talk on some of the benefits and downfalls of the slider versus the roller in each application, because it almost seems like we're going in opposite directions with the K, even though we're going from a three lobe to two lobe on the B, and the same with the K. I think there's probably some confusion as to why we've moved to a roller in the B series world and a slider in the K series world.
Well, we haven't moved a slider in the K series world.
Not yet.
So, the short summary on that is if you look at a radius pad on like a sliding type of system, the radius is obviously a lot bigger than the roller. The bigger that tappet radius is, the more area I can get under the curve. But then when you have a sliding system like that with a big radius, then like there's certain lift points where the angle's not right and it wants to wipe itself out. So that would be like pressure angle type of issues.
Your current B series offerings, especially with that new rocker arm, the slider pad rocker arm, do you have kind of a prescribed these camshafts with that system before you go to a roller? You've got all that laid out for your end users.
No, we actually we're in the process of creating different recipes for people to use.
On order, listen up. 12 covers table 23, the 12 top. 4 spaghetti, 2 risotto, 2 scallops, 3 crab, 1 Caesar salad.
Yes, chef.
I mean, a lot of people use a lot of our cams out there successfully. And everybody has a different preference, and everybody's going to swear one's better than the other. But in terms of the B series stuff, the Pro 1 stuff is really good, but if you talk about reliability for these extreme all-out drag racing type of applications, the TLRC, a big part of designing that was reliability, because the B guys, it seems like cam reliability is an issue.
Yeah.
It doesn't help that they put a ton of spring pressure in there and lock out the rocker, and it's thrown around to like 100 grams extra. It's like 100 grams extra, slinging it around, and then double the pressure on one lobe. Doesn't like that.
Right.
The lobe would want to be wider, to hold up to that better.
Got it.
The small rocker, the small cam, the high pressure is probably just doing a great job of squeezing all the oil out at high RPMs, and metal to metal contact just starts the whole catastrophe.
Metal to metal contact. Yuck.
Did you guys take a look at that article that I sent you?
Yeah, the engine builders.
Yeah, was there anything out of there that piqued your interest that you wanted to circle back and let's say maybe reframe?
I did more on the cam grinding. Oh, besides the cam grinding, some of the cam profiler, some of the software. So understanding that the software is based on the output of the software is based on the input, and there's certain limitations that are set by the person designing it. I guess my questions for you are: do you use some of the profiling software to true up your math to know that it's going to make sure that you're within certain defined realms, and then you go outside of that based on your know-how, prior experience, other forms of motorsports? Like, how much influence comes from the profiler versus your own cam knowledge?
There's no like profile library, if that's what you mean. Like cam
The
software.
cam design. So we don't really have, and I haven't, and I'm not sure how much Jay has had. In some of the cam design software, what are some of the inputs and outputs? And I'm not sure. Maybe we can walk through that, or if that's proprietary or whatever the case may be. But
Oh, well, you have all the critical you have all the critical dimensions of the geometry that's needed to translate the valve motion back into the cam motion. Critical inputs would be like ramp height, ramp speed, ramp length, max acceleration, max deceleration, or the negative acceleration number. And then you have all of these variables on the opening side and the closing side. Right? A lot of these things, it's not like I don't set this is my max. I'll measure the stock cam and see what the stock cam has for max. Right. And kind of respect that and maybe iterate, kind of like what I did on the 2JZ cam. I said, okay, that's what they're doing. Let me see if I could optimize it and make it more reliable and better performing. So like on the 2JZ cam, I actually had a better cam with a lower accelerations. I don't know if you remember that, Jay.
Yeah, I do, because the way that the system is going to open and close the valve, respecting longevity, respecting the flat tappet design, trying to avoid, I believe you called it
Nose radius.
seating velocity, and
Yeah.
we talked about seating velocity and nose radius. That's kind of why I wanted to go back to that valve motion page and just like as we summarize camshafts, um, we have a situation where when someone looks at the valve motion page, they say, okay, there's the take up ramp, there's the nose radius, there's the seating velocity, all those things in one place.
Is there a graph that shows that? There isn't a graph that shows that, especially if you're talking about the details of the ramp. That's more like looking at the numbers on the design screen or the analysis screen. Because it's like the lift and the duration will drive everything, right? So like if I have a certain lift and as I start reducing the duration for the same lift, all the accelerations will come up, positive and negative. So then the question is, what is the ultimate limit of the positive acceleration? I've explained that before. On a finger follower system, it's radius of curvature, right? Can the cam grinder grind it? So whatever
Because
the
of the
limit,
grinding wheel size, correct?
literally the grinding wheel size will determine your your peak acceleration, your peak positive acceleration limits, right? The negative acceleration, or I gotta.
Speaking on the cam grinder wheel, cam grinding is not something like everybody under the sun now has a CNC machine. Everyone can CNC something, they can 3D print something. How common are these performance cam grinders locally here and even internationally? Like on a scale, like how would you like is it a specialty type thing or are there a bunch of cam grinders out there?
Well, there's a lot of manual cam grinders out there, right? So you have, like Webb, Delta, Crower, uh, Brian Crower, like a lot of different people. Like they have Burco or Storm Vulcan or Van Norman cam grinding machines, and that's really just a grinder with a rocker table on it, so they can just sort of like grind the cam like they're copying a key.
Mhm.
But how many people can actually design it from raw measurements and numbers? Not many. Like most of the places that do the manual cam grinding and the regrind stuff, they have a catalog full of profiles, right?
Yeah, they have like the masters
Right.
ropes they can rely
But
on.
then you don't know what the geometry was for that associated profile, right? And that becomes really sketchy on the rock arm stuff. Ugh, this is the bane of my career. In the V8 world, you have certain cam guys, and we know that they're actual cam guys. But in the import world, you don't have that. I could not sell this in good conscience. It really boils down kind of to the ethics of the person selling them the stuff.